Okay, so we're in 1.3 now, and 1.3 is a really critical section because we're introducing the concept of a matrix in this section, and linear algebra is very, very much concerned with matrices. We kind of frame most of the concepts that we talk about in linear algebra around this concept of a matrix. And we're going to, throughout the course, kind of develop our idea of what a matrix is even for. But to start with, we're going to define it in very abstract terms. Maybe abstract's not really the right word. We're going to define it in a way that doesn't really give any hint as to what they're used for, which I know is kind of unsatisfying at first, but it's going to be better if we sort of develop that idea of their usefulness as we go. So what is a matrix? Well, the simplest definition is that a matrix is a rectangular array of numbers. For our purposes in this class, by numbers, what I mean are real numbers. But in the wider scope of things, they don't actually have to be real numbers. In more advanced classes, if you take a second course in linear algebra, you find that when we look at matrices that have complex numbers as their entries, there's actually a lot of really useful and really awesome theory that comes along with that. But typically in a first course, we don't delve quite that far. They can belong to other sets as well. But for our purposes, the entries of a matrix will be real numbers. Now, we've sort of dealt with matrices already. We've talked about augmented matrices to represent linear systems. But that's a matrix that's used for a very specific purpose. And for us, we don't necessarily always want a matrix to be an augmented matrix. Sometimes those columns and those rows don't necessarily represent unknowns or equations. So we're going to keep things very general, and we just think of it as a rectangular array. Now let's talk about some of the terminology in a matrix. So first of all, every matrix has what we call dimensions. Dimensions are just quantifying the number of rows and columns. So for example, if we say that we're dealing with an m by n matrix, what we mean is that it has m rows and n columns. Number of rows comes first, number of columns comes second. This matrix right here, for example, these are all examples of matrices. It has 4 rows and 2 columns, so I would say that this is a 4 by 2 matrix. Similarly, I have a 2 by 2 matrix right here. This would be a 1 by 4. Each entry is the only entry in its corresponding column. This would be a 3 by 1 matrix. This would be a 1 by 1 matrix. Okay? Now, matrices of these types here, pay close attention to these two actually, are important enough that we give them special names. So an n by 1 matrix, which means it has n rows and 1 column. The 1 is kind of the important thing here. If it only has 1 column, like this one, then it's a matrix, but we also assign it the name column vector. So this is a matrix that we would call a column vector. If it's a 1 by n matrix, so in other words, 1 row and any number of columns, we call that a row vector. That's this. So if it looks like 1 row or 1 column, it's a row vector or a column vector. A 1 by 1 matrix is, we don't encounter these that much, but when we do, we will usually identify this as being equal to its entry. Now, what do I mean by that? Well, this, normally, when you look at this, you wouldn't say, oh, that's the number 6. I would normally say that's the 1 by 1 matrix whose entry is 6. We think of a matrix and a number as 2 different entities, right? But for purposes of simplifying a lot of the work that comes later, it turns out to be really useful if we just say, yeah, even though this is a 1 by 1 matrix containing the number 6, I'm just going to think of it as the number 6. So we typically do that with 1 by 1 matrices. Okay. Now, the real numbers that we're using as entries in our matrix, we're typically going to call those scalars. In fact, anywhere in this class that you see a single just real number used or referred to, we're also going to call those scalars. The reason for that will become more apparent later on. We need to get used to the notation that we use for matrices as well. So typically, if we want to talk about a specific matrix and we want to assign it a name to refer to, like a variable of sorts, we're going to give it a capital letter most of the time. Row vectors and column vectors are usually an exception to that rule. We oftentimes will use lowercase, but we'll bold them. So this is a column vector, it's a matrix, but rather than use a capital letter, I'm using a bold X to represent this. Also, notice the subscripts that I'm using. If I'm trying to speak in general terms about a matrix, so if I'm saying here's some general m by n matrix, the subscripts are going to tell me the row and column that an entry is in. So it's a way of identifying its position. For example, right here, the 2, 1 here, that's not a 21, that's a 2, 1. It's telling me that this entry is in the second row, first column. Second row, first column, you can see that here. That's a common notation that we use. Okay, now you're going to see that when we're working with matrices, in particular if we're trying to prove properties of matrices, it's extremely cumbersome to have to draw this thing or write this out every time, because whatever property or whatever it is that we're trying to prove may require us to write this matrix multiple times. And so we're developing some notation here that's going to simplify the amount of writing that we have to do. So this matrix right here, if say A is equal to this big mess, I can simplify that notation by just saying A is equal to, and then in square brackets, Aij, lowercase aij down here. I is the row, and J is the column. So if I is equal to 2 and J is equal to 1, then I would be referring to this column right here. Okay, but by doing this, A equals the square brackets, Aij, then not only am I assigning the capital A to the name of the matrix, but I'm also identifying how I want to represent my entries as lowercase a's. Okay. Oftentimes, we will write this without specifying what the actual dimensions of the matrix are, because usually that will be mentioned somewhere else in a proof. But if you need to mention the dimensions of the matrix somewhere, you could put it as a subscript right here, m by n. Okay. Well, you'll almost never see me write this here because we'll mention the dimensions somewhere else. Another notation, and you're going to see me use this notation a lot in proofs, is this. If we have specified that we're talking about the matrix A, so capital A represents a matrix, if I use parentheses around A, and then I put Ij outside of that as a subscript, this is another way of identifying the entries of the matrix. So if all I've done is said, we're talking about a matrix capital A, and I haven't made any reference to its entries as lowercase letters, I don't need another type of symbol to represent the entries. I can use this parenthesis here to represent the ijth entry in the matrix A. Okay, so that might be a little bit confusing now, but we're going to use that a lot, and hopefully you start to get used to that idea. Okay, so what if, let's talk about some more terminology. If you have an n by n matrix, meaning you have the same number of rows as you do columns, those are a very special type of matrix, and we do a lot with those. We call them square matrices for kind of obvious reasons. Same number of rows and columns. If you think of rows as like the height of a matrix and the columns as like the width of a matrix or something, then same height and same width looks like a square, right? If you have a square matrix, then these entries, the 1, 1 entry, the 2, 2 entry, the n, n entry, all the ones where the row and column number are the same, we call that the main diagonal of a matrix. Now, in this notation, it might be a little tricky to visualize that, but what we're talking about is the entries that you see as you go from the top left to the bottom right along this diagonal. See the 1, 1, 2, 2, and so on. This is not a square matrix, so it's not necessarily terminology I would apply to this one, but hopefully you get the idea. All right. We consider two matrices, A and B, to be equal if two things are satisfied. One, the dimensions have to be the same, so you can't have a 3 by 2 matrix being equal to a 3 by 4 matrix. That would never work. Their dimensions have to be the same, and their corresponding entries have to be equal to each other. So the ijth entry of A should be equal to the ijth entry of B for every choice of I and J. Let's take a look at this example. For which values of x are these two matrices equal to each other? Well, we can see that they're both 2 by 2 matrices, so their dimensions are the same. That's the first thing to check. Second thing is we need corresponding entries to be equal to each other. So here, this is first row, second column. My 1, 2 entry here is 0, and I can see that it matches. My second row, first column, my 2, 1 entry is a 1, as is this. So I don't need to do anything about those. We need the 1, 1 and the 2, 2 entries to be equal to each other. In other words, I need 4 to be equal to x squared, and I need 16 to be equal to x to the 4th. Okay, now this is easy enough. I can solve this by taking square roots. X should be equal to plus or minus 2, and those are the only values of x that would satisfy this first equation. You can check for yourself. Both of these, the positive and negative 2, will also satisfy the second equation. So that gives me the full set of solutions. If x is equal to either plus or minus 2, then that would give me 2 equal matrices right here. Okay. All right. Now, if you have 2 matrices, A and B, with the same dimension, we can add 2 matrices. So what we're going to talk about now is some of the different operations that we can perform on matrices to produce new ones. How does addition work? Well, first of all, like we said, the dimension has to be the same. Otherwise, the addition is not defined. And we define addition this way. The ijth entry of the matrix A plus B, so A plus B is the new matrix that we get, is equal to the ijth entry of A plus the ijth entry of B. In other words, and again, this notation might be confusing to see here. In other words, what we're doing is we're taking corresponding entries and adding them. It's very straightforward. Same thing with subtraction. So the difference between 2 matrices, if I want to find the matrix A minus B, I take the ijth entry of A, subtract the ijth entry of B, and that becomes the new ijth entry of the matrix A minus B. And again, with subtraction, you also have to have both matrices being the same dimensions. So very quickly, we can do an example here. A plus B. What would A plus B look like? Well, first of all, check that both matrices have the same size. They're both 3 by 2 matrices, so we're good there. The end result should also be a 3 by 2 matrix. It should have the same size. And I get my 1, 1 entry by adding the 1, 1 entries here. Negative 3 plus 0 is negative 3. 0 plus 2 will be the next one. That's 2. 1 plus negative 5, that's negative 4. And then 4 plus 8, 12. Negative 3 plus 0 is negative 3. And then finally 6 plus 12, 18. Okay? Really straightforward. It's just addition. And hopefully from this process you can see why you need these 2 matrices to be the same dimensions. If they weren't the same dimensions, then there's going to be an entry in one of them that has no corresponding entry to the other one, and you can't add that. Same thing with subtraction. Let's look at subtraction. So I'm subtracting. Negative 3 minus 0 is negative 3. 0 minus 2, negative 2. 1 minus negative 5 would be 6. 4 minus 8, negative 4. Negative 3 minus 0, negative 3. And then 6 minus 12, negative 6. Okay? Subtraction is very straightforward, just like addition. Okay. Another operation that we perform on matrices is called scalar multiplication. Remember, we said that a scalar is the term that we use for real numbers in this class. So we can multiply a real number times a matrix, and that's called scalar multiplication. So how do we define that? It's defined pretty much exactly the way you would expect it to be defined. This is the notation for it. So CA, everything that appears in parentheses is the name of a matrix. The matrix CA, its ijth entry is going to come from multiplying the ijth entry of A by the scalar C for every I and j. In other words, if I have a matrix A and I multiply it by a scalar, it's just the same thing as multiplying all of its entries by that scalar. Here's an example. So using matrix A from the previous example, we want negative 4A. Let me write out what A was. Negative 3, 0, 1, 4, negative 3, 6. I'm multiplying that by negative 4. Okay, I just multiply each entry by -4. That gives me 12, 0, -4, -16, 12, -24. That's it. Okay, very straightforward. Nothing fancy about that. Okay, let's see. Yeah, that. All right, let's talk about partitioned matrices next. So partitioned matrices is basically just a notation that makes representing matrices a little simpler. What we mean by a partitioned matrix, if I have, for example, this matrix right here, which is a 3x4 matrix, I can split this thing up into what are called sub-matrices. So notice if I were to put a line through here and a line here, I've split this thing into 4 parts, right? The first sub-matrix, which is this little guy right here, is a 2x3 matrix, 1, 0, 9, 2, 5, -2. I can call that a 1, 1. Being the, if we think of the sub-matrices making their own big columns and big rows, it's like the first big column and the first big row. A1, 2 would be this little guy right here, 4, 10. A2, 1 would be this row vector, 6, 4, 1. And then finally this 1x1 matrix down here, which only contains the number 1, I would call that A2, 2. So if I name those sub-matrices here, then I can say A is equal to this. Notice I'm referencing only the names of the sub-matrices here without referencing their entries. This has a number of benefits, and for our purposes, we often won't partition matrices quite in this way. In more advanced classes, you see that a lot, but in this class, when we partition a matrix, usually we're going to be partitioning it into rows and columns. So you'll see this. Suppose you have some matrix A, and you've specifically stated these are its columns, C1, C2, C, all the way through Cn. So it has n columns total, and we've given names to each of those column vectors. Then you could write A as being equal to this. Now, if you look at this matrix, it looks like a row vector. It looks like it's a 1x(n) matrix, but it's not. It's an m/n matrix, and that's because these are not entries. These represent entire columns. We're just not writing the columns out. Okay, so you have to remember that. The bold here is kind of our clue. Similarly, if A has rows R1 through Rm, then I could partition the matrix A this way. And by partition, again, it's just a notation that simplifies it in a way that might be useful for something. So A is equal to R1, R2, and so on. This is not a column vector, even though it kind of looks like one, because these are not single entries. They're entire rows that we're using a short notation for. Okay? All right, I think this is a good place to end this video, so we'll pick up on the next video talking about matrix vector products.